Thanks for the introduction, and thanks for everybody for coming. So let me get started. I would be saying a bit about what we have been doing in the lab and a bit about, I see lots of probably grad students here, a bit about what are the superconducting qubits and what they're meant to do. The other way. So the idea of simulating nature probably goes back to Richard Feynman and his vision that he had to use nature to simulate nature. But I think I want to start by asking a question that probably is in your mind, but you're just too shy to ask it from me, or that, where is it? Where is this quantum simulator or quantum computer that we have been promising for, I don't know, maybe more than a decade now, and we don't have it, right? Probably you guys want to know the answer, why we're getting taxpayers' money and we're not delivering anything. What happened? Where did money go? I think if you go back and read Richard Feynman's original work, he knew the original of the difficulty, and he referred to it, and he said it's a hard problem. So I want to explain to you why it's a hard problem, and he know exactly it's going to be hard, and he know exactly it's going to probably take time. What we are trying to achieve in here is to control individual degrees of freedom of a quantum system. And there are many, probably polynomial number of them, and they would control an exponentially large Hilbert space. And he knew that's going to be hard. So after Feynman said it, the many platforms, I guess, in recent years have been developed to kind of solidify and envision that research and make it to happen. But none of them has been delivered something that you cannot do in your computer easily at the moment because of what this problem being so hard when it comes to control individual degrees of freedom. And that's why we're in business and still haven't delivered. So, but you might have another question in your head on, which platform to choose, right? You are in the beginning of your PhD studies and want to know what is the platform to choose, right? Usually people ask us. I tell you what platform to choose. What platform would be promising. The platform which would be promising is the one that passes this test, okay? What is this test? This test is as you scale up the system, we make many more quantum degrees of freedom, you don't lose control over the system, meaning that you're going to go up straight. And that is going up straight is what Feynman had in mind. If you come down and you scale to a large system and you don't make good control over the system, then probably you are not what Feynman had in mind, and you're back to conventional condensed matter physics since 1911, when we saw mercury going superconducting. We had many degrees of freedom, but very small control over them. And this is not what Feynman had in mind. So I think this is really the big criteria, and that's why these platforms are kind of trying to achieve, and that's why it's hard. And whoever platform you think can do it this way, then I think it's going to be a winner in the next few years or so. But also there's other issues. Other issues being like you have to able to measure it. You talk to theorists, they're crazy asking for about weird correlations. You have to be able that your platform allows you to measure those strange or weird correlations that they are after. And also you have to have coherence. The requirement of coherence is easy to satisfy if you isolate your quantum system, but then you use control. The requirement for control and coherence kind of go in opposite direction, and there's a trade-off. You can isolate a quantum system and it can have minutes or hours quantumness, but that's not, again, what we had in mind. You have to be able to maintain coherence while you have control over individual degree of freedom. So that's the origin of the challenging, and that's why things are difficult. So this is one way of making qubits, okay? There are a couple of other different ways of doing it. By now you should be very excited, want to be doing it. So let me just tell you a possible way of making the quantum qubits, a quantum platform. And that is by using a Josephson junction and shunting it with a capacitor. Essentially, Josephson figured out that if you have two superconducting islands separated by thin insulator barrier, then the relation between the two superconducting phase between the island, if they're different, could lead you to essentially a current. And this is essentially would act as a nonlinear inductor. The nonlinearity is very crucial in here. And then if you shunt it with a capacitance, you have an LC oscillator. The difference between an LC oscillator that you can buy from an electronic store and put it together is that this is nonlinear, and that's really the key. So the nonlinearity would lead to unequal level of spacing. If you had a linear harmonic potential, you would get an equal spacing. That's the cyan curve. But then the nonlinearity gives you the level of spacing gets more jammed together, so it gives you the addressability of the level. And people focus in these two lowest level, and they call it qubit. So this is how the device would look like in real life. You put an aluminum on a piece of inert substrate, sapphire, glass, silicon, doesn't matter much for this talk. And then you start the lithography process, you carve a pattern, and then this is the capacitor of it. This is where aluminum is. The black is where aluminum is removed. And then this is the junction. You zoom in here. This is the Josephson junction, this nonlinear inductor. And then this is a zoom-in view of, you see aluminum oxide, aluminum. That's where the junction is. So that's the object. And okay, so I'm going to show Hamiltonian. If you don't care, don't bother. It's for theorists. So I brought some of it for you. And the reason I'm going to this is I'm dedicating to. This is the work which the thesis is done, Julian Kelly Nature paper in 2015. I'm giving to some science center in here. This would remain in Singapore. But this one I brought, but the reason I'm passing, and this one is before when you dice and you get lots of chip. I pass it around. So I think if you guys come with a tweezer, I can give it to you at the end, or 12 of them or so. But this may not look very bright because there is a resist on it, but feel free to explore it. Also, I brought this tool, so you turn it on. You feel like an actual scientist. If you're a theorist, that's your chance. Yeah, right. And this one, this is a 9 qubit in it. The reason I'm showing this is that you can see that the quantum degree of freedom is macroscopic in here. The atom we are talking is really large, and that's actually good. It's very important because as I keep lecturing, you want to couple to it. You can't couple, okay, maybe you can, but I cannot. You rotate it. Right, okay. Theorists, please don't leave fingerprint on it. I got fingerprint of many people. How did you do? Okay. Right. Sure. And then this is important to, I show you how it looks like, a zoom-in view of it. But it's important. You can see when you cool it down to millikelvin, the quantumness exists in like a 0.5 millimeter length scale. And that's very important because you can couple to it. You might be clever to figure out how to get an atom and bring the various controlling it is on block sphere and then bring another one, but we are not that clever. So we make things big, and we think big is good. Not too big, but big enough. So for those of you who are interested, this is the Hamiltonian of the single qubit. This capacitor. This is a junction. You put two junctions for technical reasons, so you can tune it. There is this cosine as opposed to phi squared. If it was just phi squared, it would have been a linear. So up to here, essentially, is harmonic. Is a linear harmonic oscillator. And then these higher order terms, the expansion of the cosine is where the juice is where the nonlinearity is. And then you use rotating wave approximation, go to rotating frame. You see the nonlinearity leads to these U-terms, Hubbard U-terms, and you, let's say you get clever enough to figure out inductively couple two of these guys, and you have some coupling which looks like flux-flux coupling. And then again, you use rotating wave, you get this hopping rate. And you put it all together, you get the Bose-Hubbard Hamiltonian as a model for the system. So if you didn't understand what I just said, it doesn't matter. Just remember that we have Bose-Hubbard Hamiltonian. Okay, so I have to now explain that where this is coming from. Huh? How do you couple to? So maybe we can understand that part. Essentially, we want the flux in one qubit, the circulating current, to be related, to be coupled to another one. You can think of them as a variometer. That's the idea we did. The idea is you put another loop between the two qubits, and then this would act as a variometer. Okay, if you're hearing the word variometer for the first time, variometer is like two solenoids inside each other. You pass current through one, it goes through the secondary one. But if you change the relative axis of them, then the current, the flux may not go through, and then you get zero coupling between them. Where the relative angle is zero, flux on one of them is not going to penetrate to the other, right? So the idea in here, in this loop, you have a junction, and you can put flux into this loop, and essentially this will become an open circuit or closed circuit, depends on the amount of flux you're putting in here. And then this allows the two to be coupled to each other. So essentially, you know, if you have two linear oscillator coupled with strength m, the frequency of them would split with a value of j, and then you just do simple math of how much current you put current in here. There's a inductive coupling, and you go do the math, and you put it together. You arrive at a very simple relation between the coupling strengths between the two. And this is actual data showing that when you put flux into this loop, the magnitude of the frequencies gets split. This is a frequency difference. And that's what we're going to refer to as hopping strengths, or the coupling strengths between the two qubits. That's how you do it. And the important point is that it goes positive and negative, so you can really turn it off. So you can go along this curve, put flux in a nanosecond time scale. You can put flux in here, and you can go from 0 to full strength and such. And that is that's how we control the qubit. So this is the chip, as big as the other one, where the experiment is done on. It's about 1 centimeter across, and you see like about 28 lines coming in to control the various parts of the system. These let's see what's the next image. Okay, it's a zoom in view to it. Here, right, this is the wires coming in. Let me just zoom into the center. You see this is the capacitance of the qubit. It's just painted red, so you can see it's just aluminum separated from this ground plane aluminum. And these figure 8s are these variometers I mentioned. And these lambda over 4 resonator is a resonator which is frequency shift depending on the state of the qubit. So you use this to read out the qubits. And then these lines are used to control the quantumness of the individual degrees of freedom of qubits. Essentially, you see there are 2 lines coming for each qubit. This is to control x, y, z. So when you do a block sphere, right, there's x, y, and z. One line is used for x, y, another is used for z. This line is to control this term, the hopping rate, the coupling between the qubits. So essentially, every term in this Bose-Hubbard model, which I said, we have control over, and that's why these lines coming to the premiere of the object, except this nonlinearity, which is fixed by design. So this would be our goal every time we make chips. We're just going to be not losing full control. That's not something we joke about. This is what we are very serious about. So essentially, another zoom-in view of this, and this model of the variometer I explained, you can see more clearly color-coded in here. Lots of details goes into this, lots of complicated fab, which we keep trying to simplify, but it's a very delicate object to fabricate. But I think the take-home message is that first, we have control over every degree of freedom. Second, is large, and large is good. Okay. Some parameters of the system, the coherence and such, but the dynamic I'm going to show in the system is going to be way shorter than the coherence times, that we're not going to get worried about the coupling to the environment, the coherence of the system. Okay, so we have a problem in mind to solve. I'll get to that problem, what it is. But first, I want to tell you the spectroscopy method that we invented to study this problem. You might be interested to know the energy eigenvalues of a Hamiltonian. So you need to invent a spectroscopy method. So we did that, okay? And then it became obvious why we did that. It became relevant later on. So let's say we're interested to there is someone gives us a Hamiltonian, and we want to know the eigenvalues of it, eigenvalues of Hamiltonian, meaning eigenenergies of the system. So the method we came up with to do that, it's like is very could be intuitively understood as what we call hitting a bell. Essentially, you can know the fundamental frequency of an object by listening to it. You can excite it. You can, any object, you want to know what are the frequency of its oscillation, fundamental modes. You can hit it, and then you can listen to it. And then your ear can do the Fourier transform, or you can sense it, or whatever. So it's about 40 hertz or so, 400 hertz, sorry. And then you can hit it again and say, oh, okay, I can hear two tones in here. Maybe there is another tone at 500 hertz or so. And then you hit it enough in the many different places. Then at the end, you convince yourself that you can capture all the fundamental modes of the problem. And that's the essence of the method. Essentially, this is what we have done in here. But I'm going to be getting more rigorous about this. It's not as hand-wavy as just explained. Essentially, what we realized was that according to Schrödinger equation, the wave function of a system evolves with this relation, which means that there is the energy eigenvalues of the problem appear as a phase that accumulate, and these are the eigenenergies of the eigenstates of Hamiltonian, the many-body eigenstates of the problem, where this is eigenvalue equation. So when you look at it, essentially, it pretty much looks like a Fourier transform relation, right? This is saying that if you record this guy and Fourier transform, you get this, roughly speaking. I'm going to get more accurate about that. And that is the essence of this hit it and listen mechanism. Okay, so let me show you how it works. And probably you have several questions in your head on how it works, but I make it clear how it works. Be patient with me. So at first, let's say you have 9 qubits. And then you hit it. You excite 1 qubit. This is the action of hitting it. Here, you put an excitation into the system. Then you turn it to the Hamiltonian of interest. There's someone told you is interested in certain value of mu, n, and j. You just turn on to those values. You just turn it on, and then you stop it every whatever nanosecond, and you listen. That's the action of listening. Don't worry about that. That's just for tomography, reading the state. And then you listen, and then you go a little longer and listen and record again. That's the action of listening. This is the measurement, is the action. So what do you record? You record sigma x and sigma y. Okay, I get clear why you do that. And then you just keep listening how these two operate, how these observables x and y evolve as a function of time. You can choose anywhere in this place any qubit to listen to it. That doesn't make any difference. And then you combine them with this clever combination. You x plus iy is going to get clear why soon. And then you Fourier transform it. So this is the signal you make. This is your time domain signal. And this is the Fourier transform of it. It says that when qubit 8 was excited, this is the Fourier transform. The color is the magnitude squared of the Fourier transform. So this is the frequency or energy of the system. And you see certain peaks. Okay, it's good. There are some peaks. But if you're experimentalist, you know that you Fourier transform anything, you see peaks. That's not a big deal. So say, okay, what can we do? You repeat the experiment. That's the action of hitting in other places and listening. You hit in different places. You excite qubit 1, 2, 3. And you see some of the peaks appearing exactly at the same place. And that's very encouraging. That says that, genuinely it seems we have been finding some frequencies of the system. So you do the most naive approach, and that is you just add up these things. You Fourier transform, amplitude squared, and you just add them up. And when you add them up, you see some of the peaks are really standing taller than the others. And then you claim these are the eigenvalues of Hamiltonian, eigenenergies of the system. But again, if you're an experimentalist, that's not hard. You Fourier transform, there are 1,000 peaks. You can call them whatever you like. That doesn't mean that you found the actual eigenenergies of the system. So now I would prove to you that we actually know what we are talking about, okay? So we just assign this guy to be the first eigenenergy, second eigenenergy, just coming from addition in here, nothing fancy in here, right? Okay. But let me close a couple of loopholes before proving that actually we know these are the eigenenergies of the system. First of all, you would say, look, you don't measure wave function in the lab. You measure observables in the lab, right? You measure operations that are observables. So let's just see what happens if you do that. Let's say we are interested in observable O, which has this decomposition in the energy eigenbasis. These are the eigenenergies of eigenstates of Hamiltonian. And then you see how O, expectation value of O of t evolves according to this relation. And you see you get the energy difference. And that is disaster, meaning that if there's 9 eigenvalues into the problem, you get every couple of difference of so you get 42 choose 9 of peaks in the problem. That's really bad. This is when I saw this, I just got very upset, and I called Girowatt, and that was end of me. So, but then this is so you just if you're you got to get clever in here. You got to get clever so you don't get all these peaks of differences. So I was not clever, so I collaborate with someone clever. That's how I solved the problem. So essentially they told me that if you pick this E alpha to be fixed, then it can come out, if it's fixed for every case, for every run, then it can come out of this summation and you're okay. And luckily in the Bose-Hubbard ladder, there was this manifold of photon number 0, which was not evolving. And we based everything on that. Okay, I'm really damaging the picture, but you can fix it if I'm really doing. So and then this is really where you base it. I'm going to make it more clear. But then from all these also, not every operator is going to work. You have to be clever in the choice of operators. For some operators relate within a manifold, some operators go between a manifold, and we're going to focus on an operator which takes us from this to our destination manifold. Okay, let me look at this table. You can choose different operators, observables to look at. You can choose different initial states, but if you're not clever, 70%, 75% of the time it's not going to work. Only when you choose the proper initial state, which has, you see this 0, 0 to it, this, based on this zero photon manifold, which is not evolving, like not accumulating phase, and you choose the one which connects this one to upper ones, and that's only where it works. Otherwise, you get nothing or energy difference, you're screwed. So there are tricks in here. You should read the supplement of the work, essentially, that you can see that not everything works. And because there are 2 tricks, definitely I couldn't come up with this. You have to really think hard to figure out how to do this. So, okay, believe me now that we don't get energy differences. We get absolute energies with an overall offset, which is the same for all cases. So now I owe you another thing. I have to prove to you that what I claim to be the eigenenergies of the problem are actually the eigenenergies that I had in mind. Otherwise, these are just 9 tallest peaks, okay? So we pick a problem. The problem is interesting. It's related to motion of electrons in a magnetic field. If you get a 2D plane and there's a lattice and electrons move in the presence of magnetic field, one length scale would be the hopping. They would be in the angstrom scale for the electrons. Another length scale would be the cyclotron radius for free electrons. And if these 2 lengths scale become commensurate and incommensurate ratio of each other, you get a very interesting spectrum. And in 1970s, Douglas Hofstadter figured that out. And that 2D electron problem is non-interacting, can be mapped to this Hamiltonian, where the role of magnetic field is played by this B parameter. So this is coming from my laptop. Let me, okay. This is the MATLAB code which generated that. There is nothing done. You just look at this 150 by 150 matrix. You diagonalize it. Let me go back slowly. You choose a value of B, you diagonalize this matrix, 150 by 150, nothing fancy, and you get a bunch of 150 dots and you put them up here. And then you go to next value of B, you get them done, you put it in there, and it looks like butterfly, simple, few lines of code. But because it's beautiful and it has this fractal pattern and contour set, people were very much in love with it since whatever time Hofstadter said it. But then they realized to make this two length scale commensurate, you need about 10,000 Tesla, which we don't have, at least in US. So this is the range which is accessible in the lab. There's really nothing. Okay, you're not going to see this whole beauty. So people worked hard, came up with different techniques. One was then you have 2 layers of graphene, and then you can define a super lattice, and you can get features consistent with having the Hofstadter butterfly spectrum. But note that they cannot do a spectroscopy. They just measure the resistance, the transverse resistance, or Hall conductance, and they say it's consistent with having a Hofstadter butterfly as underlying spectrum. So that's the state of the art, and this is the few lines of code which did it. So, but this is what we can do in the lab. We can do 9 qubits, essentially. So this is how things would look like if I do my things properly. So here is the magnetic field, and then we are going to solve this problem or implement this problem, do our spectroscopy method, and then we're going to get 9 peaks, right? And we're going to put dots. Still, this is done in the computer, but if you hold your breath, I'm going to show the actual data that when we did it in the lab. Okay, so this is what we expect to get. And this is what we got in the lab. So you go to each magnetic field, meaning that every value of that B parameter of the Hamiltonian, you do your spectroscopy, you hit it 9 times, and you get a bunch of Fourier transform, you add it up, and you put a line in here. And then you go to next value, and again and again. So let me go back and forth. Try to lock your eyes to some feature and see how reproducible it is with compared to where it is. You know, look at some feature in here. And see where it shows up. So it's pretty darn good. I'm going to get more qualitative about it. But, you know, it looks like a butterfly, right? It's not. So probably we did it right. So let me just be more, get more quantitative about this. So here I went and I look at every value of magnetic field. I look at the 9 tallest peaks, and I put a dot when I saw a peak. And the gray line is where I set it up. You know, it's a 9 by 9 matrix, so you can diagonalize it in a matter of seconds. So this is the gray line is where I expect the peaks to be. The dots is where I found the peaks in the actual data. And the color of the dots is where is how far is the difference between the dot and a gray line, right? If it's really off, if it's dead on, you get black. If it's off, you get red. That's how much the deviation, absolute deviation from peak identification to actual gray value. So you see we get lots of black is good, and then green, and then sometimes we get red. The red sometimes is misidentifying a peak, so we can do a better job, but I didn't bother. So you just add up all these colors. You know, what's the error in average? You get about 3 megahertz, somewhere in here. This is the average of all these colors. And so in the spectrum, which is 300 megahertz in bandwidth, we have about 3 megahertz in average. So about 1% error when you do this thing in a very continuous dynamic. So we have very good understanding of the capacitance and inductance of the system. And we can set this problem. This is a manifestation that we kind of know how to set the parameters of the system precisely to a very good degree, to a very good approximation. Okay. So, so this was showing that we can set the Hamiltonians, and for I didn't mention it, maybe I amplified now, that usually people think that doing gates may be the only way of moving forward, but you can see here that also you can apply continuous quantum dynamics and study the quantum dynamics continuously. It's hard to benchmark, but also you realize that it could also work to a good degree. And this would be way faster in terms of creating a highly entangled state, which I would get into next. And that's where we are. That's where we are focusing next. I get to the many-body case next, but I want to say that there are other approaches besides gate-based, and has its own drawbacks and issues, but I think it's very promising if you know the parameters of the system. And the accuracy of this is resting on the fact that we could do a spectroscopy of individual qubits and know the capacitance and inductance, and this model that I draw really is a reliable model, essentially. Okay, so this was all calibration. This was all things that we could do, and I want to show you a physics problem that could be interesting to all of us as a physicist. How would you go and solve that? The whole statistical mechanics that we study is rest on this fundamental assumption of statistical mechanics, which says that all accessible states of the microstates of a problem are equally probable. And this just assigning equal probability to each microstate is enough for a theorist to just go and compute all the parameters of the system, all the pressure and pressure and other variables of the other quantities of the system, and be happy with it. But an experimentalist want to know how this is actually happening, why they are equal probable. And Boltzmann himself was bothered by that, so he came up with H theorem, and I'm super simplifying history in here. And says, came up with something ergodic hypothesis. They say if you have ergodicity in a system, you're fine. You can use fundamental assumption, and you can assign equal probability and just go ahead and be happy, have a happy life. But then, okay, we are left with the systems question of what systems are ergodic, what systems over time explore all their accessible Hilbert space or all accessible phase space. It turned out in classical system, when you have chaotic dynamic nonlinearity, so hypersensitivity to initial states, then the system is chaotic. And if its system is chaotic, then your ergodicity hypothesis hold, and then you can expect that you can get thermal distribution and you're fine. But what if ergodicity breaks down? There's one very well-known case that ergodicity breaks down, and if the system is too symmetric, and you might but that's a very fine-tuned scenario where you're not going to explore all its available Hilbert, all available states because it's just too symmetric, and you're just going to go over certain trajectories, and some parts which are energetically accessible is not going to get accessed. So we know these examples. Like if you have a motion in a stadium, if you just wait for enough time, bouncing from the wall, you're going to eventually cover the whole accessible space, in this case literally the two-dimensional space. But sometimes you don't get to their ergodicity. And that is, as I said, this fine-tuned case, for instance, when you're bouncing in a circular billiard table where no matter how much you wait, you're not going to get to certain parts. So this didn't bother theorists or experimentalists in a sense much, because they said, this is a very fine-tuned problem. But there was another scenario, and that was when the system is interacting, Anderson came up with an idea that when there's disorder in the system, disorder could lead to localization. And then there would be absence of diffusion, the system would not thermalize. And that did not bother experimentalists or theorists or no one that much. They said, well, that's fine, but when you have interacting, no matter how weak is the interaction, you might not get thermalized, and you might get stuck. If you have interaction, this is not going to be the case, and you're going to get thermal states. And in 2006, Basco, Aligner, and Altshuler, again, history super simplified, they said that, well, maybe that's not the case. Maybe diffusion, maybe propagation of energy and thermalization fails in interacting, even in interacting systems. And that kind of started making people worried, and they wrote many papers, and people start to do experiments to see that. And it seems after some work of these guys, it seems that could be the case, that in spite of having interaction in the system could fail to thermalize. So And then you look into this literature, you see that for this transition is not a quantum phase transition. It's transition from where a statistical mechanic is applicable to where it's not, from where ETH holds to where it doesn't hold. There are these predictions for it. You look at the level of statistics. You look at the spatial extent of the wave function, or you look at the two-point correlation. So these are the predictions that they said would show some signature of this transition, and that's what I will be showing you next. Okay, so if you were careful enough up to this Hofstadter butterfly, the interaction term was off, so was non-interacting, and it was kind of would not maybe interest some of you, but now we're going to turn on this interaction by putting more photon in the system. Before, n was either 0 or 1, so this term was 0 anyways. But now we're gonna have this term. But again, you need to measure certain. You have to put several photon in the system, and then you have to listen to it. And this is where this part happens. You measure certain correlation. Don't ask me why these correlation and why to combine it with these prefactors. What can answer that? But essentially, this is the magic. And there is some pattern to this madness. It's not that bad. You look at the supplement, they tell you how to do it. It's not the only thing you can measure, but it's probably the simplest thing you could measure. So you read these two-point correlations. You add them with these. They look crazy in real time. You record them, and you add them with this prefactor, and you Fourier transform them. And this is the Fourier transform in here, and then you see that this is which qubits, where the photons were put initially, and this is the energy, and you see peaks. It's hard to make it out. You can take my word that there are 45 peaks in this pattern, roughly speaking. Now the error goes higher. It's not really, it's not that simple to see that, but then you can roughly count this, and it's about 45 peaks. Or at least what we're going to do, we're going to call the top 45 peaks as the eigenvalues of the problem, eigenenergies, and then continue with that. Okay, so that's very simple thing to do. So, so level of statistics, the very eminent dominant prediction about this phase transition was that when you have many-body localized case, the level statistic, the distribution of levels in energy would obey Poisson distribution. However, when the correlation is strong in the system, the level of statistic follows something called GOE. Okay, let me guess. Gaussian orthonormal ensemble. It doesn't matter. So they obey this statistic. The R obeys this statistic. Okay, what is R? According to Hughes and Oganessian, and among others, R is this thing that you have to consider. So these are the energies of this is the energy, and these are where you find the peaks, okay? From energy differences, S, you define R with this relation. My contribution to the field was to give a name to this R. I call it level separation uniformity. It tells you how the levels are spread in energy landscape. Essentially, when the levels are correlated, there is something level repulsion. They elbow each other out of each other's path, each other's vicinity. And they tend to be more uniformly spaced. But when this order is very strong in the system, the correlation would not be sensed, and every energy level would act independently, would not know any knowledge about any other energy levels. That's a random distribution, which is the Poisson distribution. That's where the origin of Poisson at high disorder limit, a many-body localized phase or state. And this is okay. The example to keep in mind is it's like a bus schedule, right? In some places, maybe California or places that public transport are not good, the arrival of the buses are not correlated. You get a bus, God knows when's the next bus. But then in some country, I don't know, I'm not going to comment about things I don't know enough, but in Japan or Europe, the bus is correlated. You miss a bus, you know there is no bus for the next few minutes. The presence of the bus, arrival of the bus at the station is correlated. And there is actually a paper about that. You can go and figure, I'm not joking. So, So let's just focus on the dotted lines first, the dashed lines. The dashed line is just plotting this function of R. It says that the Poisson distribution would look like this. This is in the extreme limit, thermodynamic limit that theories live in. And then this is on the GOE would be like this, showing that R alpha is closer to half or something, 0.4 in fact. The dots are extracted from data in two different choices of disorder over hopping strength. A value of U is fixed. And you see that one case would look like more like Poisson, another would look more like a GOE. And the solid lines is the simulation for this small system, right? I have only 45 levels, and I repeat the experiments 4 times or so. So you're not going to get exactly Poisson. It has all these features to it too. So that's what we got in here, okay? And you see it's kind of okay matching and whatnot. So, but let me get more precise with this. There you go, that's the references. So the color is the probability distribution histogram of R alpha being the level separation uniformity. You see at very low disorder, the correlations are dominant in the system. R alpha, the peak of the histogram is close to the middle. The levels are pushing each other out. They feel each other. They don't like each other. And then when you increase the disorder, they don't care about each other. The disorder is dominated. Everyone acts independently. And the peak of the histogram will go toward lower values of R alpha. And that's what this plot is about. Okay. Okay, there is another nice finding comes from our spectroscopy method, which has been close to the heart of condensed matter theories for many years, and that is participation ratio and inverse participation ratio. It's a very intuitive concept, meaning that when the wave function gets localized, it would not be spread over many lattice sites. And this can be really easily extracted from our data. Let me show you how. Essentially, we want to know the spatial extent of an eigenvalues of the Hamiltonian. We do that by focusing on the amplitude of the peaks. Now that we have identified 9 peaks, we can go and see what's the amplitude of each peak. So far, we were so much concerned on where the peak happens on the energy axis. Now I'm going to focus on the amplitude that we found. For instance, this number, this intensity would tell you the probability of finding a 9th eigenvalue on the 6th lattice site. And these peak values, amplitudes, can be extracted and put in a table. And then, for instance, that guy comes where? 9, 6 is here. That number is that number. And then this you can add them up, and then either this way or that way, and then gives you participation ratio in a space or participation ratio in energy. One being the number of energy eigenstates that have a significant presence on a lattice site. Another is the number of sites that an energy eigenstate is extended over. So we're going to extract that from our, this is a non-interacting case. I'm trying to bring you up to speed, but then here actually we did it for the full many-body case that we have more than one photon and interacting was present. Let's start with this one. Let's try to understand this one. This is the participation ratio in energy. When the disorder in the system is low, this value is about 45 all across lattice site, meaning all 45 eigenstates of the problem, many-body eigenstates, have significant presence over all lattice sites. You go to first lattice sites, you kind of get the feeling of every wave function has some significant presence in there. And you increase the disorder, you see that the wave functions tend to go toward the center. There is less number of wave functions you would be feeling when you're at the edge of the lattice, and you would be feeling more of them. You see more of them if you position yourself toward the center of the lattice, and that's the red one, and the numbers is even lower, okay? Here the same story goes in energy. You should think about this as a band in energy. When disorder is low, you see that the first energy eigenstate, being that is very lower one, have extended over almost 9 lattice sites, the entire chain. And then it's the same is true for every many-body energy eigenstate. And then as you go higher, the energies that are located close to the band of the energy energy band, they would be extended over less number of lattice sites. And it would show this almost semi-spherical dome. You know, there is this prediction for the Anderson model. When you add disorder to a band, the states close to the edge get localized first. Those that close to away from the center of the band. I'm not sure this has anything to do with that, but it just looks like that. So, but it's easy to understand what's happening in here. Anyways, okay. But then I can also read the most obvious thing from the data, which was the two-point correlation functions, which we have Fourier transform. Let's just look at it raw value and see if we can make sense of it. And indeed, it shows very intuitive consistency with what we expect. So here you see two-point correlation functions, the classical part subtracted, and there's several summations. This is summed over time, sum over these four combinations, and summed over also lattice spacing, meaning that 4, 6, and 5, 7, all of them are kind of added and presented for this separation of 2. So here is the level lattice separation, two-point correlation between lattice that are this much distance from each other. Here is this order, and the third axis, the color, is this average quantity, essentially two-point correlation. Let's say when this order is low, the points in the lattice are as correlated as each other. There's no distance related. There's no space dependence to it. So point number 1 and lattice site 1 and 6 see each other as much as point 5 and 6 see each other. That's what this uniform distribution is, uniform color is. You increase the disorder here, you see that the points that are further apart start to not be correlated with each other. This is quite intuitive, right? They're not sensing each other. And interestingly enough, the points that are close to each other start to get more correlated. I would say that it seems that some puddles are forming and the formation cannot escape, so the nearby points get more correlated than what they would have get otherwise, essentially. But that's very intuitive. Okay, so okay, I don't know what it was. So where are we going with this? This analog method, this approach that I'm saying, continuous quantum dynamic, has the quite advantages of its goal not to be very far from what we can do now. If we could just increase our capability by not an order of magnitude, maybe twice or 3 times in magnitude, then we can really get somewhere very interesting. So I asked some of my favorite theorists, how many qubits we have to put together with this approach to do something interesting. And the number, surprisingly, is very small. If you really do good quantum dynamics and you have good control and maybe some mechanism for error mitigation, canceling some errors, not even error correction, just some data points that are very off, you trash it or something, you do some symmetry arguments, then the like 1% error I mentioned on average, if you could maintain it to a few tens of qubits, clearly according to these guys, you really approach some very fantastic land that you can do very interesting physics. And I really want to highlight the various applications they are pointing to. The numbers all about 20. They did not talk to each other, but it come about 20, except this number, which is about 100, which I think Chetan was mainly thinking about the ground state of a system. When you're talking about ground state only, there are certain tricks you can play to get the ground state. But if you think about it, this dynamic in a disordered landscape, you can't go beyond 20 or so. Maybe you get really clever, you can get 10 more qubits, but eventually it's not going to be that far off from these numbers. Okay, this is the team who made the work possible. This is the Google Quantum Hardware team, and this is the Quantum Theory team in Los Angeles. This particular work was in collaboration with Dimitris and his team. And here, but I want to tell the last minute where we are going with this. Okay, because I think with Google, people are mainly interested in what we're going to do next. They don't care what we did. They just want to know what is next. I don't know why. So they keep asking what is next. So I'm going to tell you what is next. So forget about all these 50 minutes, and then what is next? So I have a manager, that's my boss, who is kind of vague, and you can dare to ask him a question twice, and he says something, let's just double. So, okay, what the heck he means by double? What to double? So we took some initiative, start doubling, and then we show him this result that we are start doubling, and he was like, no, this is not scaling properly. We don't need to do it this way, and it was very expensive. But it was not done in the lab. He made it clear that he meant the qubits. So this is the evolution of these Gmon qubits. And you can see that with 2013, when we did this variometer scheme, which we call Gmon, it was only 2 qubits, and then it got up to 15 qubits now, and we're working on this 15-qubit chip. Okay, I want to finish kind of in an industrial tone, saying that at Google, we are clever enough to realize that we are not clever, and we need to collaboration with outside community in quantum information in general, and condensed matter and physics in general, to solve the problems. The problems of making a quantum platform is very hard. So we start establishing various schemes of communicating and incorporating the whole community of workers, I don't know, at many different levels. And you can come and ask me about these possibilities. There are people in our team who are working actively to establish these things and get connected to academic places like in here, because we truly value collaboration with outside world. And if you manage that, you come to Southern California for, I don't know, Disneyland or something, you can stop by that in our lab. I would be happy to show you around. This is where we are located. This is the University of California, Santa Barbara. This is where we originally started, and now we have a lab in town. But also, just to, is missing from this list is this award that we recently issued to work with tourists who are working close collaboration with us and come up with very practical and feasible applications to do with our platform. And we just approved and issued the first 2 winners of this award. Elliot Capit from Tulane University and Dimitris from this institute became the first winners of this award. So thank you.